Thank you for the introduction. Good afternoon, and thank you for coming for my presentation. Today, I want to show you how to use STEAM sequence in ultra-high fields, in this case at 9.4 Tesla, for acquiring high-resolution diffusion MRI in post-mortem human brain samples. Sorry. There you are. Just for a small background, ex vivo imaging in comparison with in vivo imaging possess some advantages as high resolution acquisitions. And the use of some sequences, as for example, the gradient echo or the spin echo, shows some challenges that we have to deal with during analysis. A STEAM sequence, that is the stimulated echo acquisition method sequence, is one of the sequences that we don't have to deal with these challenges. And also for diffusion acquisitions, STEAM shows several benefits in comparison with the spin echo sequences. But here's the one of the points of this work is like independently of the sequence that you're using. When we are using ultra-high field scanners 7 and above, we have to deal with several effects in our images due to B0 and B1+. One way to correct these effects is by the using of the kT points methods. As you can see here, when we are using standard sequences in 9.4 Tesla, our image, the resulting image, shows several signal dropouts, as you can see here. And this is mainly for the inhomogeneities of the effects that I mentioned before. The kT points methods, in a small overview, is the use of several subpulses that allows me to excite in a more homogeneous way my sample. And as you can see here, when we are using this method, we can recover finally all this signal that was completely dropped out, and we can also increase the signal-to-noise ratio across the entire image. So the aim of this study then is to try to extend the use of this method across the STEAM sequence, which is composed by 3 pulses, make this compensation to recover the total signal, the dropout of signal that we can see in our data. And if we can if we can incorporate these pulses in our sequence, then we can move forward and try to acquire high-resolution diffusion data in post-mortem samples. For that, we are using a 9.4 Tesla human body scanner with parallel transmission available. And for that, we are using a human whole brain coil in which is conformed with the shape of the brain that allows us to get to be more efficient in the transmission and the reception of the signal across the sample. This coil was already shown 2 years ago by Robrook et al. In OHBM. So the STEAM sequence, as I said before, is a sequence that is composed by 3 pulses. And the use of this sequence, use the global pulses, normal pulses in the 9.4 Tesla, show these inhomogeneities as I shown before for the GRE sequence. One idea and one approach that we can think about is why don't incorporate this set of sub-pulses in the excitation pulse? Should be enough. Actually, it's not enough, and actually, it's not an improvement. And it's improvement, as you can see here. So it's necessary then to extend these subpulses for all the pulses. And you can see here that we could recover the signal that was dropped out. So this sequence now, with the use of these subpulses that is now called kT-dSTEAM, since now we can recover the signal and acquire a full entire image of the brain, we can use now, we can modify to convert it to a diffusion sequence by the incorporation of 2 diffusion gradients. One is before of the second pulse and one after the third pulse. This, the way to calculate the B values is equal to the Stegner's-Turner sequence, in which we are using the gradient amplitude, the duration of the gradients, and the diffusion time, that is the separation time between the diffusion gradients. For that now, we are going to use this sequence for acquiring 1 millimeter isotropic data that takes approximately 18 minutes in the entire brain. And we are pushing the resolution that is as much as possible that the scanner can offer us to a 400 microns, in which takes already 2.5 hours per volume. In the acquisition for 1 millimeter isotropic data, we had to consider that the sample in itself can be important. For example, this sample is a well-preserved sample with a low fixation time, in which it shows doing relaxometry that we perform in the sample. We could estimate that the T2 of this sample is 22 milliseconds. With this T2 sample, for saying one way, very high T2 for the in vivo, ex vivo samples, we could achieve a very high B value of 8,000. And you can see the contrast between gray matter and white matter. Anyway, and that is one of the advantages of this sequence, even with over-fixed samples, as for example this one, in which the T2 is really lower than the other sample, we can still achieve a very high B value. Using this kind of samples, we can perform a standard DTI analysis, and you can see here that we can get a very nice distributed fraction anisotropy map. We can get the mean diffusivity map across the entire sample, in which possess a low diffusivity as is expected for ex vivo samples, and you can see the projection of the first eigenvector across as well in the entire sample, especially if you notice there in the corpus callosum and the optical tract. So now, one of the interesting points about this study is that we have now 1 millimeter isotropic data, and that is nowadays the standard goal for diffusion in vivo. Since we have the advantages for doing ex vivo studies, we can increase the resolution 10 times approximately, and we can acquire 400 microns isotropic in the entire volume. And you see that the contrast between gray matter and white matter is increased. However, increasing resolution implies that we are dealing and we are challenging with the SNR. So the maximum B value that we can achieve now is not so high as for 1 millimeter isotropic, and the SNR already at 3,000 is starting to reach the noise floor. So now what to do? We have already a coil that can perform a very efficient acquisition. We have a scanner that can allow us to get a quite high resolution images. We have a sequence that can work with any kind of samples. So we can move forward and try to explore the reconstructions. Reconstructions in itself, as you can see here, we move from a standard reconstruction, that is the sum square reconstruction that the scanner offers you usually. And we move to the covariance sum square reconstruction, in which we are taking as information the noise covariance matrix of the channels of your coil. You see for a B0 is not so much different. However, if we move to a very high diffusion weighting volume, as you can see here, we can recover the temporal area of the brain, and we see that the noise was reduced. You can think that it's just an assumption that I got because the image looks good. But if we go to the standard DTI analysis, we see that the fraction anisotropy map, the artifacts in the temporal part that we see for the source-mag reconstruction is completely reduced in the Kovsov's reconstruction. And you see that the mean diffusivity map gets more homogeneous across the entire sample. So now we can take this reconstruction as part of a pipeline for high-resolution diffusion data, and we can study how it looks like the first eigenvector across the entire sample. For example, if we take this area of the brain, we see nicely how the first eigenvector crosses the corpus callosum and crosses the white matter, reaching the cortex. And that is one of the most important points I want to remark, how well this is defined across the brain. And also, we can zoom in the corpus callosum and the cingulum, that are usually the areas that most people look when are doing this kind of studies. And we see that for this resolution, we can start to get advantage to do more analysis and to study it better, because we can have a better definition of these structures. So now I can take this information, I can take these results, I can do tractography. This tractography shows you actually a very smooth distribution of the gyri and the cerci across the surface of the brain in two different perspectives. And especially if you take one of the gyri, you can see how the streamlines are crossing radially across the gyrus crown, and it started to touch in this part with the sulcus wall. So as conclusion, and that is the message I want to give you now in this talk, is first, we can use the STEAM sequence in ultra-high field scanners and take the advantages that that sequence offers for diffusion by the incorporation for the kT points to avoid inhomogeneity problems, as I showed before. Also, this sequence allows us to get high diffusion weight and a high resolution whole brain ex vivo data. As an outlook of this, it's important to consider that acquire 400 microns take 2.5 hours to acquire per volume. So it reduces the amount of time, the amount of volumes that we can acquire to do sophisticated models. However, we try already to acquire, we acquired already 500 microns with half of the phase field of view, which reduced the acquisition of 1 hour 48 minutes to 28 minutes. That allows us in a weekend, in 66-hour scanners, to get multi-cell data that can be very useful for applying more advanced orientation distribution models and tractography. If you have any questions, I will be glad to answer. And please, if you have to have a better talk of this, you can visit my poster tomorrow in the afternoon. Thank you so much.
Okay, if you have any questions, make your way up. So 2 things that occurred to me. The first one, so with these STEAM sequences, I can see why they're so attractive, particularly at 9.4T, where you have very long T1s and very short T2s. Mm-hmm. How would you expect the performance of these sequences compared to some of the other methods to depend on field strength? Do you think that in general that this is going to be a sort of a preferred method regardless of the field strength people are working at, or?
Well, thank you for your question. A STEAM sequence for our study and our perspective has one of the advantages that, well, as I described before, the model is simpler enough to analyze. And second, the fact that we are using ex vivo samples, the parameters like T1 and T2 gets completely reduced. STEAM has the ability to, using this timing between the second and the third pulse I described before, to weight our images also by T1. So if you have a T1 around the 300, 400 milliseconds for ex vivo samples, you can define a very high B value of 3,000, 4,000, 5,000 using mixing times of 100. So you are still recovering, you're not losing too much signal when you are modifying the mixing time. Yeah. Well, personally, I see the advantages to use this sequence for post-mortem samples.
Great. And then I guess very quickly, the other question that I had was, when you talked briefly about trying to go to multi-shell, how important do you think it's going to be to keep the diffusion time fixed? Because obviously it'd be nice if when you're doing lower B values, if you could reduce the diffusion time as well, because you'll get some SNR out of that. But then it has the problem that you're not quite looking at the same diffusion process.
Thank you again for the question. One way to solve that problem is try to keep the mixing time fixed and a specific high value, and try to work mainly with the gradient amplitude, because that is one of the factors in diffusion in which it's not completely affected by the anatomy of the sample.